Welcome to the Deep Dive. Today we're dissecting a concept that's really transforming modern industry, the AI factory. And I mean, this is so much more than just, slapping a sensor on a machine and calling it a day.
Oh, absolutely.
We're talking about shifting the entire brain of automation away from the cloud, which can be miles away,
Yeah.
and putting real immediate intelligence right there on the factory floor.
That's the critical point, right? We're moving beyond just collecting data, which is what the IoT wave gave us.
Right.
An AI factory is more of a self-sustaining ecosystem. It's where intelligence, automation, and data all come together to turn what a sensor sees into a physical action.
Instantly.
With zero delay.
So our mission for this deep dive is to really define that blueprint. We want to look at the three core architectural pillars that make all of this possible at the edge.
And we really have to start with the why. I mean, why is this big push to the industrial edge happening right now?
Good question.
Well, the source material is pretty clear that the old cloud-centric systems, they just have a critical failing. They
Right.
don't have the speed, the deterministic speed, or the security you need for these mission-critical jobs.
We're talking about situations where milliseconds actually matter.
Exactly.
If you have a complex manufacturing line or a safety system needs to fire, you can't afford that round trip to a data center and back.
You can't. Zero cloud latency isn't a nice to have, it's an absolute operational requirement.
And that need for instant local decision-making, plus, I imagine, the peace of mind that you can keep running even if your internet goes down.
Precisely. That's the engine driving this massive market shift. We're seeing projections that the industrial edge market is going to more than double, something like $21 billion in 2025 to almost $45 billion by 2030.
Wow.
Yeah. And that growth is purely from companies adopting this kind of localized AI.
Okay, that really puts the stakes into perspective. So let's unpack this architecture. You said there are three pillars that kind of cover the whole life cycle of intelligence?
Right. Think of it as intelligence, validation, and management. So first, you've got the AI inference layer. That's the raw processing power right where the action is.
Okay.
Then second, you have the testing and digital twins layer. That's how you make sure the intelligence is actually correct and keeps getting better.
And the third?
And finally, the automation and orchestration layer. That's the big management system that keeps this whole distributed fleet of devices running securely.
Let's jump right into pillar one then.
Yeah.
AI inference. This is the intelligence layer.
Yeah.
This is where the factory floor hardware actually gets smart.
Yeah, this is the beating heart of the whole system. You're taking trained AI models and you're feeding them just a massive stream of sensor inputs.
It's like what kind of inputs?
Real-time video, LiDAR scans for robots, telemetry from machines, all of it. And the model has to make an immediate decision. The goal is always deterministic, low-latency performance.
So in that case, study about inspecting glass vials.
The parenteral vial inspection, yeah.
Right. That system is watching a video of the vial and has to decide in a split second if there's a microscopic crack.
And if it has to wait for an answer from the cloud, the whole line just grinds to a halt. It's not an option.
But pushing that kind of heavy computation to the edge, that must create some huge engineering challenges that, your standard office PC could never handle.
It does. I mean, think about it. You're running these complex deep learning models on GPUs inside a little sealed box on a factory floor.
Right. You've immediately got three problems. The sheer data volume, the need for that low latency, and then the biggest enemy of all electronics.
Heat. Exactly. Thermal stability becomes a mission-critical feature.
So how does the architecture solve for that?
Well, it shifts completely. To handle the scale, you need modularity.
Yeah.
This is why you see things like these specialized edge boost nodes. They're not just simple ports.
Okay.
They're actual physical modules that let you add more power as you need it, like another GPU or high-speed PCIe cards or more NVMe storage.
So the intelligence can actually grow with the task. You don't have to rip and replace the whole computer.
Exactly. It's a huge win for the people building these systems. And then you have to connect all the sensors, the cameras, the control systems, the LiDAR.
They all speak different languages.
They do. So you need these edge boost I/O modules. You need interfaces like PoE to power the cameras, CAN and COM for the industrial controls, and GMSL for those really high-res synchronized cameras you see in robotics.
And all that performance has to be sustained, often in a place that's dusty or vibrating or just plain hot. So how do they solve the heat problem in a sealed, fanless box?
This is the really clever part. The chassis itself becomes part of the cooling system.
So it's not just a box.
No, it's an active component. It uses a conductive design, usually aluminum, with copper heat pipes inside. They pull the heat away from the chips and spread it across the entire surface of the enclosure to dissipate.
So it basically turns the whole computer into one giant rugged heatsink.
Precisely. And that's what lets these systems run consistently across these insane temperature ranges, like from -25 Celsius all the way up to 70 degrees C.
Wow.
That kind of toughness is what makes deploying AI for something like, say, accelerating AMR deployment even possible. Consistency is everything.
Okay, this is where it gets really interesting for me. Let's move to pillar 2. Testing in digital twins. So we got the intelligence, but that's only useful if you know it's correct. And safe. This is the validation layer.
A digital twin is, well, it's a high-fidelity virtual copy of a physical machine or even an entire process.
And it's fed live data from the real thing.
Continuously. It lets your team see exactly how an AI model is behaving under all kinds of simulated conditions.
So you could, what, throw poor lighting conditions at it?
Yeah.
Or a rare production error?
Yep. You can simulate high-risk scenarios safely without ever stopping the real production line or breaking anything. It creates this continuous feedback loop. By comparing the real world with the virtual model, engineers can find performance gaps. Maybe the vision model is only 98% accurate when the lights are dim.
I see. So you can then tweak it in the simulation.
You refine the decision thresholds, you validate the improvements in the twin, and then you push the secure update back to the physical system. It makes learning continuous and completely risk-free.
But running a simulation that's that realistic, that has to take a massive amount of processing power, right? Isn't that just moving the problem from the cloud to the factory?
It is, but with a critical difference. You have control over latency and your data. Yes, the computational demand for realistic simulation and replaying sensor data is huge. You need industrial GPU computing for that.
But you're keeping all that compute local.
Exactly. You keep sensitive operational data right there on premise, and you eliminate the latency. And since you're running these intense simulations, data integrity is everything. A power loss during a test could corrupt hours of work.
Which brings us to another one of those clever features, the ECO supercapacitor backup systems. How do they fit in?
They're critical. Unlike a battery, a supercapacitor gives you an instant burst of power to handle a flicker or a full outage. It protects the testing data and lets the system shut down gracefully.
And they're maintenance-free.
Which is huge. It guarantees you can keep your validation work going without worrying about replacing batteries. So you have the industrial GPUs for the simulation, you have high-speed NVMe storage to replay the data, and on-prem AI servers to securely test and retrain the models.
It's a whole architecture just for iteration and resilience.
It is. It's how you can do things like optimizing paper filler automation, where testing a new algorithm in a twin can save you millions in wasted material.
So what's the big picture then? We have intelligence making decisions and validation making sure they're the right decisions. The last piece is pillar 3, automation and orchestration, the management layer.
And this is arguably the most complex piece. Because once you go from one AI system to a whole fleet of them, dozens, maybe hundreds, spread across different sites, you need a way to see everything.
You need unified visibility.
Unified visibility, streamlined remote updates, and just ironclad cybersecurity. This layer manages, secures, and monitors the entire distributed fleet.
Logistics of that,
Yeah.
it sounds like a nightmare, especially if a machine loses connectivity. Production just stops.
Which brings us to a really important innovation here. Out-of-band management, OOB.
Out of band. Explain what that means for, say, a factory manager.
It means you have a dedicated, totally independent, secure back channel to control the device. It operates completely separately from the main network.
So even if the main network is down.
Even if it's completely down, OOB gives you a secure remote lifeline to recover the system or push over-the-air firmware updates. It's compliant with tough security standards like IEC 62443.
That's a game changer. So instead of flying a technician out to a remote site to reset one box, you could do it instantly.
Instantly and securely. And that need for speed also means you need resilient communication, which is why 5G-ready computing is becoming so important. It gives you that low-latency link between all the machines.
Okay, let's talk security. The more devices you have, the bigger your attack surface. How do you lock these things down?
Security has to be built into the hardware from the ground up. You rely on features like the Trusted Platform Module, TPM 2.0. This isn't software, it's a dedicated security chip.
A hardware root of trust. What does that actually give you?
It gives you protection at the deepest level. The TPM can detect if someone has tampered with the firmware before the system even boots. And critically, if someone physically rips out the storage drive to steal data, the TPM makes that data unreadable.
So the security is part of the silicon itself.
Exactly. It's essential for managing a secure fleet. And of course, you still need human oversight.
The HMI, the control dashboard.
Yes, that's where you see things like ignition-ready edge computers. They run the software that creates those SCADA dashboards, giving operators a single real-time view of the entire factory's health.
This whole AI factory architecture, intelligence, validation, and orchestration really is a complete cohesive ecosystem.
It is. It totally transforms what industrial autonomy can be. I mean, from route planning for robots to high-speed quality control, the applications are just vast.
I think the biggest insight here is that this signifies a really profound shift. The reliability of modern industry isn't just a software problem anymore.
Not at all.
It's fundamentally a hardware problem. It depends on this rugged, thermally stable, and securely managed hardware sitting right at the point of action.
That's it. And I think, looking ahead, the big question for you, the listener, is this. What crucial real-time decision in your industry is still being held back by a slow connection to the cloud?
Because that bottleneck
That bottleneck is the exact target of the AI factory revolution.